Say. Okay.
40 Fahrenheit. Sun.
It's recording. It seems to be able to. You seem to be visible. You seem to be audible.
Yeah.
Someone will let us know if not. Hopefully.
Double check that.
Okay, let me summarize the ideas, especially for you, at the beginning. What is Euclidean space? By Euclidean space, we can understand a pair. Three-dimensional Euclidean space. You can make any dimension. So, like a triples of numbers and certain quadratic form, actually maybe quadratic form. And this quadratic form is defined that there exists. So the quadratic form must be such that there exists basis, coordinate system, such that Q is equal to x squared plus y squared plus z squared, but it doesn't mean any coordinate system it is so simple, okay? But there is one which is like so simple. This is connected with both ways, in a sense, with the inner product. So suppose we have here a vector v, and this vector is x, y, z, okay? So there is an inner product v and another vector v prime, okay, which is simply x times x prime plus y, y prime plus z, z prime. And then this can be written as here, let's put this vector, first one, x, y, z, transposed, so put it horizontally, okay? Then you put here a matrix. In this case, it is just 1, 1, 1, and 0 outside. If there are zeros, I'm not writing it, okay? And then here, x prime, y prime, z prime. And for you, this is like a very simple thing. Like multiply them, you'll see you'll get this one. And this is invisible matrix. But if you change your coordinate system, like from perpendicular to maybe something like this will be full of numbers. So that's why we never write it. You typically write only this, which is this, but it is there. It's typically there. Okay. So what else can we define here? That's it, maybe. And the only thing maybe is this idea of a sphere. Maybe another thing. But now, what is the connection? Q would be simply V with V itself, because it will be x, x, y, y, z, z, okay? And then we denote it as V squared, like a norm, okay? And that's it. And that's it. And with the matrix more complex, everything works. From going from here to here, you need so-called the equations, how they call them. Light can be what? Polarization equations. And from this to this, it just, okay. But then we introduce what is Minkowski space. So we'll do just mathematically, and physics of it we can do just another time, because it will be just too much to do everything at the same time, right? So it will be, we'll denote it this way. Let's say 1, 3, 1, okay? Similarly, you start with 4-dimensional, like couple quadruples of numbers, and quadratic form, okay? And this quadratic form there exists, so what sort of? Such that there exists basis or coordinate system, such that Q can be expressed as x squared plus y squared plus z squared. And if I add plus t squared, that will be just Euclidean space. This minus changes into like really different geometry. So that's what we call Euclidean space. And again, there exists a basis, but in some other basis, this might be more complex. And then by copying this idea here, it is connected with, pair with V times V prime, with the inner product. Two vectors producing a number. So if there is a vector V here, and it will be x, y, z, and t, this will be x times x prime, or x1, x2 if you want, plus y, y prime, plus z, z prime, minus t1, and t prime. Okay, so that's the inner product. And again, it can be written this way. Start with v, okay, I will repeat it, x, y, z, t, Now matrix, and then again x, y, z, t, prime, 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 prime. And this has to be transposed, so horizontally. So if I put here 1, 1, 1, 1, that will be the same thing with the plus. So to get this minus, your matrix of the inner product or norm must be like that. Okay? And sphere. Sphere, I didn't draw sphere here. Sorry. Q is 1. It will be a unit sphere, and you know that it looks like this. Right? And this means this plus this squared is 1, so radius 1. Now, here sphere, we can pick up that Q is 1. And if you draw it, unfortunately, the drawing might be tough. This is T, this is maybe X, Y, Z, because we don't have a space to draw four-dimensional space. But that thing would be, notice if T is 0, this is a circle. If T is bigger, the circle is also bigger. So this is like in calculus 3, you learn how to draw it. So it looks like this. It's hyperboloid. And here is the model of the hyperboloid, right? So, but notice that now you have a choice of being 0. Here, Q equals 0 give you just 1 point. Here, Q equals 0 will give you this as a sphere. So this is sphere of radius 0, you can say. Okay, so it's a conic. And then what about Q minus 1? This is not radius, this is radius squared in a sense. So minus 1 also exists, and again, this is like a homework for Calc 3. It looks like this. Hyperboloidal things, they're of course infinite, but there's a little piece of it. And you can draw them all in one picture, okay? So that's what is Minkowski space. Now, we will use, so convention. We can make plus, 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 minus, or minus, 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 plus, which is irritating for people who are raised in Euclidean space. But if you're a physicist, you prefer time to be positive. Because what is space? Okay, so the community of physicists is divided. Right, so more theoretical, like here, minus, 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 plus, and I also do. So with apology, let's go to minus, minus, plus. It takes a little while to get used to it, okay? So our Minkowski space, this is another version, space, version 1. This is version 2. As a personal judgment. So what do we have? We have M, this double thing, 1, 3. See, so this is like 3 positive, 1 negative. So here is 1 positive, 3 negative. So this is again, quadruples of numbers, as a naive maybe version of it, with a quadratic form. I use the other brackets, such that there exists basis, such that Q is, and we reverse it. Okay, simple thing. And just repeating it. Now this is connected with this is like maybe dot. Inner product, that V times V prime, the inner product is a number. And again, if V belongs here, it is still the same, X, Y, Z, T. And then this will be just X times X prime minus Y prime minus Z prime plus T prime. And what else do I need to know? The matrix. So we put here X, Y, Z, T, then a matrix, and then X, Y, Z, T of the other guy. And what should be the matrix? Just minus 1, minus 1, minus 1, plus 1. And if you multiply it through those matrices, you'll get exactly this. Spheres, same thing. So actually I can draw those spheres now attached to this place And what would be the difference? Oh, let me draw. Q is 1 would be this. Right? This is time. This is the X, Y, Z. Q equals 0, same thing. And Q equals -1, that will be this beautiful hyperboloid in this phase. Right? So they're just reversed. Does it matter? Physically, not at all, because just model a model, right? Some people claim, oh, if you know what it is, Clifford algebra will be different for this and for this. But you know something about Clifford algebras? Many people I find confused. Actually, you take the even part of Clifford algebra. So this means an even part of this and this Clifford algebra are the same. So it really doesn't matter. But that's for people who know and don't worry that this is not the same stuff. So, any question now?
No.
You'll have to send it to me because I finally managed to do it like nicely.
These pictures are beautiful.
Okay.
Yeah, you do good.
Okay. So you know why I drew it this way? Because now I can erase that stuff.
Yeah. Planning.
Planning ahead, right? Okay, so that's our Minkowski space. Now we learned it, just mathematical construct. Now you can forget it. Now, second thing is, so this is part 1, right? Now, part 2, which we did last time, I suggested if you have a disk, maybe like this, and another disk, maybe bigger. So notice that here the tangent lines to this and to this make certain angle gamma. And let me remind you what we did. If this is disk A, or disk A and B, so we introduce A and B, how we can call it? Maybe separation index. There's no word for it, right? So, but let's put it separation. Because I want to keep it separated from the other notion, which happens to be almost the same, but you want to equation that this is the same. You're going to keep it separated, so from 80s. So we defined it as a cosine of gamma because you can. But then remember we did this. You use the cosine law, and notice that this gamma versus this, which is the difference. They sum up to 180. So cosine of this will be minus cosine of the other one. It's like really the same. But we choose gamma, and then we realize, oh, this is the distance between the ends, and this is R1, radius 1, radius 2, and we realize that this can be written as, we have to write the law, right? D squared, right? D squared minus R1 squared, minus 1 arm, minus the other arm over 2 R1, R2. That will be the cosine from the cosine law. We have done it already. But look, if they intersect, same thing. But if they don't intersect, this doesn't make sense, right? But this makes. So this is a special case of this. So actually we want this to be our definition of our product. It's like a generalized cosine for not intersecting circles. Okay. So then we did a long calculations. And so I'm not going to repeat it to save time, okay? But we ended up in like a really messy stuff, but we noticed you can separate 1 from 2. So it was something like this. X1 over R1 times X2 over R2 with the minus. Remember? And then you have those notes from the last time. I can still like pause them if you want. Y1.
Oh, true.
You have them?
Yeah.
Yeah, okay. So Y1, Y2 over R2, you see, we're gonna keep them separated. And then plus a rather messy thing, it was half of, I have to look, because of the change of the sign, right? It might be different. 1 over R1 times, now x squared, this or minus this. We got x2 squared minus plus y2 squared minus R2 squared over R2. So separate it. And plus half 1 over R2, and everything is symmetrically to this 1 over R1. And then when you look, okay, messy and scary, but that's the whole beauty of it. We just redefine it, and I think we almost did it last time. Take the separation. This define this as just x1 dot. It's not a derivative, just a different variable. And this one, x2 dot, define this as y1 dot, y2 dot, and then here is half. Oh, I should come on half. This is 1 over R1. This is what? Curvature. This is curvature of the first one. So we'll denote it by beta 1. Okay. And this one, who knows what it is? But it will be something associated with the second circle. And this one is same thing, but this is beta 2 and gamma 1. We of course want to eventually understand what gamma represents, but right now it's just mess. But now look what it is. This is negative x1, x2 dot dot, negative y1, y2 dot dot, plus, let's put half in front, and here beta 1 gamma 2 plus beta 2 gamma 1. Ta-da! Okay. So this was a proof of unstated theorem. But now you see what it is. This is the inner product like in Minkowski space. Oh, no, not yet, not yet. Let's go back to this. So, again, I didn't finish here something. Do you see this? Like this one? I think like this one. So here is minus x squared minus y squared minus z squared plus t squared. Well, if you're playful, then you might notice this is minus x squared minus y squared, but here plus t plus z and t minus z. Nobody can stop you, right? So call this different new variables. This is like a new variable on the thing. Call it, what about beta? What about gamma?
Just guys. But no reason.
So minus x squared minus y squared, and here plus beta times gamma. Okay? And the quadratic form, this quadratic form, you can split it also into inner product. So maybe that's actually a very simple homework. But anyway, if you want to write it as in a matrix form for two matrices, so x, y, beta, gamma, we are in the same space. We just, okay, let me use this. This is z, this is x, somewhere here in the same level is y, right? And this is t. So x plus z, no, t plus z is beta. This is this vector, and this is this vector, gamma. You see, so the change variables from this to this. Such things are called isotropic because the length of this vector is 0, length of this is vector 0, so we can call it isotropic coordinate system. Okay. So anyway, so we know, here.
Could you repeat that part about the isotropic? For the latest thing is because of the length is 0?
Yeah.
Okay.
So isotropic means 0. So vector isotropic is 0 when it is like along a cone.
Okay.
So in physics, they call it isotropic, most of the time in physics. But here, not all of them are isotropic, 2 of them. But this whole thing is called isotropic because 2 of them are 0.
Of length 0.
Of length 0.
Okay.
Yeah, the vector is not 0. Big.
Yeah.
Right. Yeah, you have to associate the length of the vector with vector being big.
Mhm.
Length is just the norm squared, could be anything. So do you, here. So notice that this should be like this, -1. I'll put here just, this is transpose. This is X, Y, Z, T. And here, beta, beta gamma, right? So this will give you -x² -y². And here, beta, you want to multiply by gamma. And this gamma, but by this beta. And to get only one of them, this will produce two of them. So let's put it half and half on the skew diagonal in this little square. It will be exactly this. And this gives you, of course, an inner product. If I put here prime, you have an inner product. Okay, so we have this inner product exactly this. So our theorem is that this is an inner product in the disks, right? In the space of disks. Okay, so this was just how to get the idea. So here is the idea. He gave us this definition. These are disks, all disks in R2, in the Euclidean R2. And there is a map mu from this into Minkowski space. Which one? This one. 3, 1. Okay. Defined the following way: that the circle, let me just draw this, not circle, but the disk, with the maybe coordinate system. This is X of the center, Y, and the radius is R. We can call it disk center at X, Y, with the radius R for short. We'll never use it, but just for this thing. It goes through this map mu into X dot Y dot beta gamma, okay? Which we define, just looking from that this is simply X divided by R, Y divided by R, 1 divided by R, and here this horrible gamma, so I don't have a space to really write it, but you know. Okay, so that's a map. And the theorem, simple theorem, okay, theorem is that the separation AB between two disks is the same thing as take A to this vector representation, the other one, and use here the inner product of used in the Minkowski space. So this is here, disks, highly nonlinear, and so on. Suddenly everything is linear. You have a space, you can add vectors, subtract, you can multiply, and you get an inner product. Okay. Now I posted something. Okay, so that's the central notion of the whole thing. Like for instance, I put the paper by Lagarias and other people about circle beyond Descartes and so on. They proved the theorem, the Descartes theorem, and extended all this, but they didn't use this. They did something else. I realized, no, this is the central. The other one will get it as a simple implication. But a lot of stuff can be done with this, even beyond the Descartes theorem. So that's what I'm saying. This is the central point. To know the disks, if you want to draw here something, okay, here is a plane. In this plane, there are circles, okay, or disks. And we have this map mu to the linear space, four-dimensional linear space. Each of them is a vector, 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 vector. The map mu. Okay. Okay, now we have to see what follows out of this. So number one would be, I don't know, maybe first an example of a circle. What do you think? The names of it, okay? So this would be coordinates let's say call them reduce, because you divide by R. So it's like really positions of the center, but reduced. This one we'll call, oh, we already know, this is curvature. And some people would call such a thing a band, not to confuse with the curvature, Riemann curvature, but slightly different. And this one, well, I called it co-curvature. And I think people accept it. So, and we'll see why this could be called co-curvature. So, proposition maybe one. A few points. Number one, yeah, which one should be one? Like maybe this. The length of any such vector is -1. So for any A in disks. Aha. So look, we have now disks and their vector representation. They should be used with different letters, right? Like I don't want to write every time mu of this, mu of this, mu of this. So if this is A, here the vector would be bold A, but I can do this if you want. What do you prefer? Or maybe the arrow above. But the writing will be bold. Suggestions?
Bold is hard to see on the chalkboard, so.
So maybe with a head.
Yeah, sure, that's a nice.
Head's okay.
That's
So for any A, this, the representation of vectors we want, okay? Number two, if you have two circles which are tangent, or disks, which are tangent of different size possibly. So this one is A, this is B, then A, inner product of A and B of those vectors will be +1. Let me put here plus, make it clear, +1. What else? 3 is something simple. Suppose they intersect such that this angle here is a right angle. I'll put 90 degrees, the ancient way, okay? Then A, B are orthogonal in terms of this Minkowski thing, okay? Proof. I'm very simple proof, but let's do just everything,
Oh,
okay? So proof of one. So we just do this, A with A. Here we are, right? This minus this. Now let's go here. The distance from the circle to itself, 0. So let's mark it like that. So using this, it is 0 minus radius of the thing is r squared. Radius of the other one, which is actually the same disk, is also r squared, divided by 2r times the same r. You see this is just 2/2 minus 1. Okay. Number 2, for this external part, look at this. This is radius. This is radius of the other one. The distance is r1 plus r2. So this means that AB in such a case is r1 plus r2 squared, that the distance, minus r1 squared minus r2 squared, divided by 2r1 r2. So you don't have to go to this like Excel, just from the very beginning. And can you quickly calculate it? This is r squared and r2 squared, subtract. And it will be plus 2r1 r2 divided by 2r1 r2. Answer is 1. Okay. The third one, let's use just obvious thing. What is cosine of 90 degrees? 0. Okay, that's it. What are the resulting corollaries? Number one, you see this? All circles, let me see, okay, corollary. In this space, all disks are on that hyperbolic of the negative norm squared. Right? So it's not just any vectors, only these vectors. Now, this hyperboloid, it is a sphere in the space, right? So this is like, you know, okay, we'll talk about this maybe later. But anyway, so they are on it. And another thing maybe, all right, that would be the most important thing. And that we'll use a lot actually, that they are tangent from externally, it is just +1. Notice that it doesn't matter how big they are. This is what is funny, right? You would think like it's just always 1. Okay, next step. Next step would be to understand gamma. So what is gamma?
The Greek letter, I think.
You're so.
What is
A
that?
Greek letter, I think.
Yeah,
Third
right.
of the alphabet.
Yeah, so that's the answer. No, I just didn't want to write, to take your time to say, what does gamma represent? This is shorter, but thanks to discussion, this is even longer. Okay. All right. So gamma, gamma, let me remind you what it is. This is x squared plus y squared and -1 over beta. By the way. This is one thing. Because notice, oh, this is just another maybe result. You see this thing to be -1. So maybe first, remark. If you write this equation in terms of alpha, beta, gamma, so x dot squared plus y dot squared, either way, plus minus plus beta gamma, it is -1, right? So suppose you have x, y, and beta, because they're easy, you can read them off from the position of the thing. Gamma would be simple algebra. So if beta is non-zero, if you worry that, oh, I don't know what's happening here, how to produce this vector, produce the first 3, and the 4th one, shows up this way. Okay. But now let's go to the question: what is gamma? So Greek alphabet, you said, proposition. The meaning of gamma. Gamma, okay, is the curvature of the image of the disk, because we're talking about gamma of a particular disk, so I can use D, right? The disk under inversion through or by, everybody says it differently, a unit circle. Okay, so inversion is like not everybody knows about inversions. Who feels like okay? You don't? Okay. Okay, so I'll tell you what is inversion. So and maybe here educational corner. Okay. Inversion. How to think about inversion? So maybe first inversion through a unit circle, because only we need this one for now. So I don't have to tell you about everything about inversions, but think this way. If this is 0, this is real numbers, this is 1, -1, and so on. If you have an x, you can go with x to 1 over x. Like half will go to 2, or 2 will go back to half. Right? Just going both ways. Like 1/3 will go to 3. 1000 will go to 1000. So this whole thing is swapped with this infinite thing. It's one-to-one correspondence. And 0 goes to infinity, right? And what about negative half? Go to negative 2. So that's the inversion of like numerical inversion. Let's call it numeric. But then you want to maybe make it like generalize it to 2 dimensions. So you see this one was a special point, it goes on top itself, right? Then everything goes. So let's make instead of 1 the unit circle. 1, 1. And then define that this point, where should it go? Just outside, like here, goes outside to the point such that how do you write here an equation that if this goes to x prime, the equation is this x times x prime is 1, right? This means x prime is 1 over x. That's the equation. So let's do the same thing here. If this is that this distance is say d, and call this distance d prime. That's our x and d. So we want d times d prime to be 1. So there's the inversion through the unit circle in plane. So every point that points on the circle go to themselves. This point goes twice farther. This point 1000 away will go to 1000 in this direction and so on. Okay, so that's the inversion through the unit circle. That's enough for now, at least, about inversions. And then we claim that gamma is a curvature of the. Okay, so let me put it this way. Big one unit circle. Okay, a big theorem, which I'm not going to prove it now, but I'll put maybe some notes, so you can learn about inversions. A theorem is this, that the images of a disk is a disk. It's a beautiful theorem. So anything here, if you take every point of this and go outside, it will be just bigger disk. How to prove it? It will take us like the rest of the meetings. I'm not going to prove it like even later, but now accept that this is a standard knowledge. Actually, you can get it from complex analysis, same thing is happening, right? So look at this. Suppose I have here a disk. Every point of this of the circle will go somewhere here. Okay. Now again, suppose this is the distance of the center of the disk from 0, and here is the distance of the other center. So let's call it d prime. See, this goes to that. How can we use this equation to find out something? So notice that where does this point go? It will go there. You see this? Because it's closer, it will be here farther. So this means that b minus r, see, b minus r times d prime, oh, well, yeah, okay. Maybe, no, let's do this. D prime plus r prime is distance. This is not the center, but the thing has to be, if you multiply by d plus r, has to be 1. And another point would be, I'll make a little square. This point will go here, they're closer, right, to the mirror. It's kind of like a mirror. So d prime minus r, right? And d same, okay.
Shouldn't the signs be flipped?
Okay, here this one, d prime plus r prime, goes to this one, so minus. And minus goes to plus. Okay? Now calculate out of this system of equations, let's say r. And I've seen people struggling, so I'll show you how you do it like effortlessly. We just write this way. D prime plus r prime is 1 over d minus r. D prime minus r prime is 1 over d plus r. Okay. And now, just subtract. So this minus this will give you 2r prime. And this minus this, well, there will be this minus this, so it's a fraction. Common denominator is the bottom times the bottom, which happens to be d squared minus r squared, right? Minus r. And upstairs will be d plus r minus d minus negative r, so it will be 2r. So we got this part, right?
No. Okay, now you can. We are leaving.
So okay, now wait for this. So look, r prime is r, and here d squared minus r squared. So means 1 over r prime. That will be the curvature of the image. Okay. It is, well, you have to flip it, d squared minus r squared over original r. Ta-da! And what is d? D is the x original distance of the center from the from center of this from the center of the coordinate system. This is just x squared plus y squared minus r squared over r. Ta-da! So we got the represent. What does gamma represent? So once again, the original, this was here. I'm now converting the order. This one, if you go this down and see the image of it,
Yeah.
the curvature of this will be gamma. So that's why I thought co-curvature would be a good name.
Yeah, it's a transformation or something.
Yeah, right. But anyway, so we now see the geometry of this nice stuff, okay? All right. I think it will be time to find some examples, right? Okay. I don't know. You don't like numerical examples, so you start to feel what it is about, okay? So yeah, let's do maybe, okay, here is one disk. Radius is 1 in the center. This is 1. So let's put here small one with the radius half. And let's calculate their vectors. Okay, so what is the vector representing this? So something I already erased, but x, y, beta, gamma of this guy. So 1, 1, 1, 1, maybe. It will be, well, remember x over r, y over r, 1 over r, and gamma. So it will be x is 0. Y is 0. 1 over r. This is of what will be 1. And now we have to know that this squared plus this squared minus 1, so negative 1, divided by 1. Remember the quick way to get it? Negative 1. That's the vector. Remember this gamma is. What about the second one? So this is V. What about W? It's called V and W, the vectors. No, we call it them A and B, right?
Without hats? With hats.
With, right. So this is like A with heads, means vectors representing, this is A, this is B, and this is vector and vector. So what about here? What do you think it is? This x is 1.5. So I think 3 over 2 divided divided by the radius of this, which is 1 over 2. Man, okay.
Wonderful.
It's not so bad. Okay, what about y? It is 0, obviously. What about beta? The reciprocal of half is 2. So let me simplify. This simply would be 3, 0, and 2, right? 3 or half. Don't tell me you don't know. You haven't seen it. So, so what is gamma? I'll let you finish. What is gamma? Three squared is 9. Plus 0 squared, still 9. Minus 1, 8. Divided by 2, 4. That's a unit. Okay? Now, let's calculate what is this times this inner product. So let me put those numbers. One was 0, 0, 1 minus 1. The other one, let me put like this. And the other one is 3, 0, 2, 1. Okay. And how do we calculate it? This times this, right? And then this with this. So 0 times 3, so it will first negative 0 times 3. I'm just writing it so you like will in your notes remember how we got it. 0 times 0 plus half, and then 1 times 1 plus negative 1 times 2. Now your job. Oh, nobody told me this is 4.
Oh, that might change things just a tiny bit, huh?
Oh, yeah, 1/2 of 8 is 4.
So 1 times 4 minus 2 times 2, right? So what is it? No calculators, no calculators.
4
Was it
minus
one?
2 is 2,
It was 1.
and 1/2.
It's
That's
gotta be
why I
one.
say 1.
It's still too early, right?
I know, it's kind of. So you see, why this is 1? Because they're touching, you see, they're just touching.
Ah, they're touching.
So we didn't even need to do the computation. We should have
No,
expected.
we need it because I wanted you to see how it works.
Yeah.
Okay.
We should have expected.
So that's apparatus which allow us to see like the structure of Apollonian gasket, but also other disk arrangements. Like you know, it's like a pencil for circles, a well-known thing which is like never well explained. With this, it will be like actually beautiful, as you would say. The last thing, we have just 3 minutes, I guess, because you have classes and stuff, right?
Yeah, but we have classes like in 10 minutes.
We could be late, but
So just one thing, okay? Notation. X, Y, beta, gamma is a vector representing a circle. Just as a circle. We'll also write it X, Y, beta, gamma, and call it a disk symbol. This is vector. This is the same vector, just written differently, but it'll be convenient. Why? Because if you want to put into like drawings, those vectors, this long thing won't fit. This will, okay? And yet another thing is, this should be like an arrow, really. We can sometimes only put X, Y dot over beta, because gamma is already implied most of the time.
I was going to ask.
So this is like a reduced symbol, small symbol. We'll never use this word, but anyway, symbol. Why this is so cool? Because suppose you have, oh, I erased it. Okay, that's okay. Suppose you have a symbol of a disk. How do you know what disk it is? When you look at the vector, you have to recalculate and so on. No, you just do this. Position is X over beta and Y over beta. Okay, you just split it. Do you see why? Okay, because X dot is X over R and beta is 1 over R. If you divide this by this, R disappears. Okay, you just very conveniently, this is position. And the curvature, or radius, would be 1 over beta. So that's a very convenient way to write these things. And the time is kind of like shrinking. So
You should have chosen a different sign for time. Well, no, yeah, maybe.
So I think I don't want to give you this because I want you to like experience together that we will get it, and then okay. So that's the most important thing, okay. If you look at the Apollonian Universe, okay, quickly go with this maybe. But just one example, right? This thing which was hanging here some time ago. Oh. Okay, so these are the symbols. Symbol, you can calculate with this gamma, you have a full vector, okay? Now, you see this here? First, how do you get those things? That will be the next meeting. But you see 3, 4, 6, what does it mean? So when you're getting nervous, you don't use even a razor, right? So 3, 4, 6. Well, this means half, you see, 3 over 6, 2/3, and the radius is no simplification, just 1 over 6. Okay, and this is kind of easy to see. This is 1, so you see this is exactly in the middle. The height, it will be 1, 2, 3. So yes, 2/3. Because you start from this, and this is 1/6. Okay, 1, 2, 3, 4, 5, 6. This is a scientific method, a true engineering. Okay, so I think that's it for now, and we'll jump to more complex stuff soon. Do you have any requests? I started a blog, okay? What do you want on this blog? Just tell me suggestions, give me suggestions. I'll put whatever you want.
Keep it separated.
Like maybe your pictures. Send them to me or something.
Okay, it's a good thing to solve
Okay.
in this class, I guess.
It's in my head. He said it
Yeah, you
twice.
had to
Yeah.
do this. Now we have the song stuck in our head.
The never ending song or what song?
We'll start to feel it
Oh.
ourselves. Will take us like maybe 5 minutes, starting from like nothing. And we'll see how quickly you can actually feel it. And then therefore how you can program a computer.
You're gonna give us homework.
I'm good with it.
Want me to bring my laptop in next time?
If you want to, yeah, okay.
Okay. I don't think it was.
Actually use Maple.
You use me.
Maple to produce a lot of all these data. And I use typically what did you use? Pigs.
I did it using
From the lab, and it's beautiful works. Because you can always like pick the whole chunk, put it there, put it at comma, and so on. But so make it clear. So this is like a starting point to understand Apollonian Universe, and there is a beautiful stuff in this, and that's what I promise. You will see that this thing, if you raise it to Minkowski space, there will be like a huge platonic solid, like a crystal. People talk about like time crystals in physics and so on. That's a true time crystal. It's a space-time crystal, but you don't see it here. You'll see it up there. So that's what we want to see. But I want to tell you that this is just one side, and we will see more deeper, interesting mathematical stuff. Okay, thank you very much.
Thank you.
Entertaining.
That's very nice.
Entertainment.
And
Informational,
education.
entertaining.
And education.
Oh, okay.
But we're also here to heckle you. I think that's mostly what you do. Really?
Muhammad couldn't come because he's in St. Louis, and but we'll be next time.
I can't turn off the recording, but.
Oh, just unplug the computer.
Oh, yeah.